Okay, part 3 of this lecture, we're going to get, as promised, into the more of the mathematics of how we solve problems using Newton's laws of motion. Now, as we go into this, we need to discuss this idea of a normal force. Okay, time two objects are pressed against each other, the surface that the object is against is going to push back on the body with what we call a normal force. We call it a normal force because in mathematics and science, when we say something is normal to a surface, we mean that it's perpendicular to the surface. Okay, and so the normal force will always be perpendicular. This will always be a 90-degree angle between the direction of the normal force and the surface. Okay, so the normal force, we use abbreviation capital F sub n. Some books will use a capital N for normal force, but of course that's easy to mix up with the N for newtons. And so I do think the better abbreviation or symbol to use or variable to use for normal force is F sub n. Okay, again, it's always going to be perpendicular to the surface. So here we see a block sitting on a table, and of course gravity, the force of gravity, which your book uses F sub g. Remember that oftentimes, in my handwritten solutions to problems and so forth, I might use a W because it's the weight of an object. The force of gravity acting on an object is its weight. And so a lot of books will use a W, and I like to use W. But anyway, F sub g would be the force of gravity pulling down on this block. And of course, that causes the block to put some pressure, let's say, on the table. And therefore, the table pushes back upward here, perpendicular to the surface, through the object of interest. Okay, the direction of the normal force is perpendicular to the surface and through the object of interest. If the object of interest here was the table, then we would say this is the normal force. That would be the force pushing on the table. But the object of interest here, if it's the block, then the normal force is the force that's perpendicular to the surface, or the interface where the two objects are meeting, and going through the object of interest. Another important point as we get into this mathematical part of Newton's laws is to understand that this diagram over here on the left, while these sketches are important to start with in the problem so you can visualize what's going on and to start to kind of sketch in and label the forces that are acting in the problem, what we want to do is take that and turn it into a little more of a mathematical looking problem. And so we usually simplify. After we draw our sketch, this is an important part of the process, you draw a simpler diagram of this where you whatever the object is, whether it's a block, a car, a bicycle, a toy, whatever it is, you indicate it as a bold dot at the middle of your coordinate system. Okay, and that becomes the body that you're interested in. Okay, then you draw the forces acting on that body, only the forces acting on that body. You don't care, like in this case, I don't care what the block's doing to the table, I only care what forces are acting on the block. And in this case, I have the force of gravity pulling the block down, and I have the normal force pushing the block upward. Okay, and so again, what the block does at the table, I don't really care about. Okay, that would be acting on the table. So I see two forces here. They're always drawn so that the forces point away from the origin, away from the dot in the middle of the coordinate system. And when we simplify our diagram like this, as shown on the right, this is called a free body diagram, right? A free body diagram is the terminology we use for this. Okay, sometimes abbreviated FBD for free body diagram. And then once you have your free body diagram, it's of course important to label each force in the problem with a unique name. That should be done at some point in the problem as early on as you can, really, and make sure you have a coordinate system selected, which most of the time is going to be our Cartesian coordinate system with our x and y axes. Tension forces. When a force is attached, or when a cord or a string is attached to a body and pulled taut, okay, the cord pulls on the body with a tension force. It's typically what we call that. And so a lot of times we'll use a T for tensions. You don't have to. You can still use an F. It's still a force, or some other letter, any letter you want really to name that tension force. But it's what we call a tension force. And again, it's directed away from the body along the cord, right? Mainly to get the direction of a tension for it, I usually ask my tension in a cord. I usually ask myself, well, if the cord was snipped at that location, what direction would the object I'm interested in go? or what would happen, and then that tells me what direction the tension force is. Okay, so for example, as you see in these diagrams here, if you look at the diagram on the left here, we have a person pulling the block to the right. And so the tension in that rope, if we're looking at the block, the tension on the block is to the force to the right. However, if I look at the force on the person's hand, of course, the tension's to the left. Because if I cut the string, so again, my little rule for this or tip for this is, if you imagine just cutting the string here, what would happen to the person's hand? Well, their hand would go that way, to the right. So therefore, the tension's pulling to the left on the hand. On the other hand, in this particular case, I know that the tension in this rope is pulling to the right on the block. Okay, so the tension is going to depend on what object, direction of the tension depends on what block or what object you're looking at. So again, in this particular case in the middle, we see a pulley. Let's suppose the pulley is frictionless and massless, so we don't have to worry about it adding anything to the system. All it's doing is changing the direction of the rope, right, from horizontal to vertical as it goes down around the pulley. And when we're pulling with tension T, let's suppose that's the amount of force we're pulling with, again, the tension here acting on the block is to the right. On the other hand, the tension on the person's hand, the force of the tension in the rope here, is acting upward on the person's hand. So again, the tension T is the same value throughout a massless rope. That's another tip. So in this particular case on the right now, if we look at this situation over here, again, the pulley is frictionless and massless, we'll assume, and so that rope goes up over the pulley. Well, again, the pulley, if it's frictionless and massless, adds nothing to the system other than changing the direction of the rope. So in this case, as the person pulls down on the rope, that will put a tension upward on the block. In other words, if they pull hard enough, the block's going to go upward. On the other hand, if I cut the string here, the person's hand would fall down, right, or would come down faster because they're pulling that direction. And so the tension that's acting on their hand here as they pull is actually in the upward direction. So getting the direction of the tension can be a little tricky at first. It's really important to focus in on a particular point in the problem, somewhere that you want to focus on. Many times it'll be an object like a block, right, that you'll say, okay, there's my object of interest right there. Other times it may not be quite as apparent what you're supposed to choose as your object and point of focus. But once you do that, the direction of the tension on that is in a rope that might be affecting that object is easily answered by, again, imagining what would happen if that tension were to be pulled harder or if the rope were to break, what was going to happen to those individual objects. So again, as a tip, though, when we assume that when we have ropes and strings and problems and threads, the general rule is we're going to assume that these are massless threads and strings, and we're going to assume that they're massless and frictionless pulleys, unless otherwise stated. Okay, and because the mass in the string the mass of the string or rope is considered negligible or zero, that means the tension throughout the rope is going to be the same. In other words, there's no tension variation along the rope. So if the tension was T over here, the tension's T over here. If the tension was T up here, the tension's T down here. If the tension was T here, tension's T here. Right? So the same amount. If it was 50 newtons of tension, it's 50 newtons of tension throughout that massless rope. Okay? And that's because we're assuming it's massless. Now, most ropes and cords and strings are fairly light compared to the other objects in our problems. So most of the time, this approximation of them being massless or having negligible mass works pretty nicely, and it's a great simplification and makes the problem-solving process much simpler. So as we get into doing this and practicing this today, here's the general, I guess if I had to give you like a little recipe or prescription for how to solve these sorts of problems, this would be the general, simplified, generic process that you want to do each time, okay? So first thing, of course, is sketch the situation and choose a coordinate system. Right? Identify the object of interest or the point of interest in the problem, select a coordinate system, and then start sketching in the forces acting on the object that you can think of. Again, we don't care what the object does to other things in the problem. Right? That was a mistake I made early on in my physics learning. We just care about what forces are acting on our object that we're interested in or on the point that we're interested in. Okay, so we sketch those into the free body diagram. we make sure each of those forces has a unique name. Then what we do is simplify the diagram, and we make what's called a free body diagram, right? The free body diagram comes next, because that's taking the kind of the physical sketch and turning it into more of a vector math problem, right? That's the point of that part. And then step 3, we break the forces into component form, right? Write each force in component form, and we find the resultant force. And the resultant force is just the result of adding up all the forces, or in other words, it's most often called the net force. Okay, we want to get the overall push or pull on the object, so we add the forces together, and we get an x component, y component, z component, and we have a net force that we can write as an ijk unit vector, or a vector in vector component form. Okay, once we do that, typically what we do is apply Newton's second law along each dimension individually. So if it was a two-dimensional problem, let's say x and y with a standard Cartesian coordinate system, then we would add up the x components of all our forces, which basically gets us what? The x component of our net force. And so we'd say, okay, we'll take the x component of the net force. That has to be equal to the mass of the system, whatever, or object, whatever system is that you're considering, times the acceleration in the x direction. Then you take and add up all the y components of your forces, which is basically getting the y component of your net force, right? And you set that equal to the mass times the acceleration in the y direction. All right, so you solve up for the acceleration in the y direction. Again, the rule is obviously solve out for unknowns, right? If you know F equals ma, if they tell you the acceleration and you know the mass, you can figure out the force. All right, if they tell you the force and they tell you the mass, you can figure out the acceleration, so on and so forth. So it's a little bit of a game of figuring out your unknowns by applying the rules, the laws that you know are true. So again, we're generally going to apply Newton's second law of motion along one dimension at a time. If there were a z dimension, if this problem had a third dimension, a z dimension, we would have an equation like these two, but for the z direction. All right, now one of the things that's my job here is to try to help you be successful at this, help you understand this and learn this physics. One of the things I tend to do is I go back in my mind and I try to remember things that caused me to struggle when I first learned this material, things that caused me to get hung up. And one of them here, so I've got a couple hints for you for this, and that is that if the object is not moving, right, if it's not moving at all along a certain dimension, let's say the y direction, or if it's moving along that direction at a constant velocity, then obviously that means the acceleration in the y direction would be 0, and then that makes the net force in the y direction has to be 0. Okay, so in other words, if you can establish, when you think about the motion of the problem that you're analyzing, or the motion of the object that you're analyzing, if it does not change its y position, if it doesn't go up or down in the problem, if it's just sliding horizontally and staying at the same level, or if it's moving at up or down at a steady velocity, not accelerating up or down, then the velocity is constant in that direction, which means the acceleration along that direction is constant, which means the net force along that direction is constant and sums to 0, right? So an acceleration of 0 means a net force of 0 along that dimension. Likewise, you look at, consider the x direction. If the object's not moving at all in the x direction, if it was an elevator type problem, then you would know, okay, the forces in the x direction have to sum to 0. The elevator's not going left or right. It's not changing its motion left or right. It's not accelerating left or right. So if the object's moving in the not moving in the x direction, or if it's moving at a constant velocity in the x direction. For example, if you pushed a lawnmower across the grass, say you have a level yard and you're cutting your grass, if you push the lawnmower across the grass at a steady velocity, right? So you're walking along at a steady velocity, then there's no acceleration in the x direction in that case, which means the sum of the forces in the x direction would have to sum to 0. Okay, because sum of the forces in the x direction equals the mass times the acceleration in the x direction. If one's 0, the other's 0, right? If the acceleration is 0, the forces that add up in the x direction have to add up to 0. So this is really important information, all right, for solving, or tip. This is a real good important tip. They don't always point that, they're not going to in a problem tell you, oh, by the way, the acceleration in the x direction is 0 and the net force therefore in the x direction is 0. That's part of what they want you learning to understand and analyze and understand for yourself. So again, that's just a couple tips there for you and hints, and you'll see those play out as we practice some problems. All right, so let's try starting to do some F equals MA type questions. Now, here we see a problem. It's got the way we're supposed to interpret this anyway. All right, is that there's a string here at the top coming down from a ceiling, so it's tight up here, and it comes down and ties onto a knot here. And then there's another string, a different string over here, and it comes down and ties on here as well. And then we have a third string that's coming down here and attaches onto a 100-pound weight. So basically, imagine like a heavy, maybe it's in a stadium, okay? Maybe it's in a stadium and this is a loudspeaker or something like that, some big heavy speaker that they're using for the PA system in a football stadium or something like that. Okay, let's just make it that kind of a problem. So we're using 100 pounds, so we have to be somewhat careful with our units. But if we're just dealing with forces and no other kinematic quantities in the problem, then we can do the problem in pounds, right? The English unit for force is the pound, right? The international system of force is the Newton, right? But the international system is the Newton, but the old English unit for force is the pound. That's why we weigh ourselves in pounds, or we weigh our fruits and things like that at the grocery store, fruits and vegetables in pounds. Again, we're a country that's kind of caught between the old English system of units and the metric or an international system of units. Okay, so this is like, let's say, a 100-pound speaker, and we got 3 ropes all tied together here. So now, let's suppose the problem is they want us to figure out what the tension is here, and they want us to figure out what the tension is here. They want to know, like, if I go by like cable or something, whether say these are cables, what strength cable do I need, right? What strength cable do I need? If I go by 100-pound cable, will that be good enough? Do I need 200-pound cable? Do I need 50-pound cable? I got 2 ropes here, it's splitting the difference, so you might think, well, gee, 50-pound cable should be fine because we got 2 ropes. Is that the case? That's the kind of thing we need to understand, and that's what we're going to practice here in this process. So let's suppose again that the goal of this problem is to solve for the tension in these 2 ropes here. Okay, obviously the tension in this rope is what? Tension in that rope would have to be 100 pounds. If this thing is not moving at all, which is the assumption here, right? This is like something hanging in a stadium, then guess what? Nothing is accelerating up and down, and nothing is accelerating left and right. So what's that mean? It means the acceleration in our system is 0 in the up and down direction. The acceleration in our system is 0 in the left and right direction as well. This is an example of what we typically call a statics problem, right? In engineering, you have full courses that deal with just problems where things where things are in static equilibrium. Now, static means they're not moving at all, right? So in this case, this heavy object here is hanging from these ropes and it's not moving at all. So this is an example of a statics problem. And so if we want to solve for those tensions in those ropes, what is going to be the point that we're going to focus in on here to solve that? You might be tempted to think, well, the 100-pound speaker. But that's actually going to be the harder way to do the problem, or you're going to eventually find that focusing in on that object completely from the beginning is going to slow you down a little bit. The key point here in this particular problem, if we want to solve for those tensions, is where they kind of intersect. And so our key point in the problem is right here. Now, how do I know that, right? How do I know that that's the point I want to focus on where the ropes intersect? There's no hard and fast rule I can give you for that sort of thing. That's the kind of thing that you get with practice and experience. So what you have to do is you just have to solve enough of these problems and practice enough different types of problems that you'll start to kind of get that understanding of where you want to look to solve the problem. Here, because we're looking for a tension here and a tension here, and they connect here, that might be a tip or a clue that that point becomes important. And so basically, we're going to focus in on that point there, and we're going to put that at the center of our coordinate system. So what forces are we going to have? Well, we're going to have the tension force downward here, right? The force of the 100 pounds pulling downward on that rope. Or that knot. So we're basically focusing on the knot here, if you want to call it that. And then we're going to have a tension here, which is pulling which direction? It's actually going to be pulling this direction. How do I know that? Well, imagine cutting that rope. What's going to happen to the system, right? If I cut that rightward rope, this weight's going to kind of fall this way, right, without the tension in that cord. And so that tension is pulling kind of up and to the right. Likewise, the tension over here in the 45-degree angled one is that direction. Again, imagine cutting the rope here. What happens? The weight would swing this way. So again, that tension is kind of holding the block or the knot, if you will, up and to the left. So all these tensions are already acting away from each other. And so what we do now is we draw a free body diagram, and we say, okay, well, let me get that into a diagram. Let me represent my block, or my knot, excuse me, right at the center of my coordinate system like that. And so here's what I've got. I've got my free body diagram now. I have to get the angles drawn in there as well with my vectors. Of course, the weight vector is right along the negative y-axis, so there's no angles to worry about there. But notice I've got some angles here. I've got an angle. They told me this was a 45 and told me this was a 30. Well, if you remember your geometry, if you have a, well, let me draw it down, down here to make it clear. If you have parallel lines and a line cuts across them, then this angle, this angle, this angle, and this angle are all the same angle. And so is this one, and this one, and this one, and this one. Okay? So there's some geometry going on here. So we can see that if we were to draw, if we drew a horizontal axis across here, if that's 45 up here, then it's 45 here. And if this is 30 up here, it's 30 right here. Okay? So that's how we get the angles here, and we get those into our free body diagram. We also have to give the tensions names, so I gave the tension on the left the name T1 and the one on the right T2. Okay, you might want to call this one T sub L. Remember, the little subscripts are just reminders, your own little reminders of what those little subscripts stand for, and they're just reminders or labels. And so you could use T sub L and T sub R if you wanted. It's really nothing magical about using what you name your forces. It's just a matter of keeping track of them. Okay, so now I've got my free body diagram made, and I've got my angles in there. So what's the next step? The next step is I need to try to write each of those forces in vector component form. So when I look at T1 here, I have T1 pulling up and to the left, and it has a working angle of 45 degrees. Now, even though I don't know how big T1 is at this point, I just leave it as a variable. I just say, well, it's some amount T1. Right? I don't know that number yet, but it's some amount T1. And so vector T1, I can get the size of the x component by taking the size of vector T1 times the cosine of the working angle, and I can get the size of the y component for vector T1 by taking T1 times the sine of 45 degrees. So I go ahead and do that, and of course, because I don't know T1, I can't get these, I can't get a numerical answer there yet, but I can at least get the vector set up and expressed in component form like that. And when I do that, I typically draw a box around it because that's the key thing I'm interested in. I want the vector in component form. All right. So I do the same kind of thing for T2, right? Except T2 here points at a 30-degree angle and it's pointing up and to the right. Okay. Over here, remember T1, because it's pointing to the left and up, I make sure my signs in my vector there are negative positive. Over here with T2, it's over to the right and up, so both components are going to be positive, right? Both are going to be positive components. And of course, I use the same sort of rule. The size of the x component is T2 times cosine of the working angle, which is 30 degrees here, and T2y, the y component size, is equal to T2 times sine of 30. So strictly speaking, I should really have absolute value signs around these expressions and those variables in those equations, because we're really just getting the size, remember, of the vector components, and then we put the signs in ourselves looking at our diagram. Again, that's why the diagram is so incredibly important. We can always get the signs right. So that reducing sign errors is a huge step in becoming successful with this. Now the weight vector is pretty much a no-brainer. It's 100 pounds, and if I was the particle up here, the 100-pound weight would be pulling me downward here. That tension in that rope is pulling downward, and it's pulling downward with 100 pounds of force. So vector W, the weight vector, is just minus 100 pounds J. So again, we're going to do everything in pounds, and so that's basically our unit for this particular problem. All right, now so we need a little more room. So we take our three forces, T1, T2, and W, that we have in vector component form, and we write them down, transfer them over to our new working space so we don't have to go back and forth. And now what we're going to do is apply Newton's laws of motion. And his second law of motion says if we add up the forces on a system, an object, or a knot, for example, then the forces that add up should be equal to the mass times the acceleration of that object. Well, if the knot's not accelerating, right, if that place where those ropes come together is not moving or is not accelerating in any direction, then the sum of the forces should be zero. That is, if I add up T1, T2, and W, and those are the only three forces acting on that knot, okay, then they should add up to zero. They have to add up to zero, okay? Now, that's basically what we're doing here, right? But remember, we try to do it along each dimension one at a time. And so the first equation here would be like we say, okay, let's add up all our forces in the x direction, and that equals the mass of the system, or the knot in this case, times the acceleration in the x direction. If we add up all our y components of our forces, that would give me the y component of the net force, and that should equal the mass of the system times the acceleration in the y direction. So when I go ahead and do that here, and I look at my x components, I have this one, negative T1 cosine 45. I have this one, T2 cosine 30. And then in the weight force, there is no x component. So I end up with this equation. Negative T1 cosine 45 plus T2 times cosine 30 degrees equals 0. Okay, so that's my x equation. Then I do the same thing in the y direction. What are my y components of my forces? I've got T1 sine 45. I've got, add on to that, T2 sine 30. And then I have minus 100. And that should add up to 0. Because again, this is 0. These accelerations are 0. So when I add up my components along those directions, they should be 0. Okay? So now I have two equations, and take a look. Two equations with how many unknowns? 2. Same T1, T1. Same T2, same T2. So I have two unknowns in this system of equations, and I have two independent equations, so I should be able to solve that system. Okay? If you remember your mathematical rules, you can't solve, if I had 3 unknowns here and only had 2 equations, I can't solve that system. Right? In other words, to solve a system of equations, you need at least as many independent equations as you have unknown variables. In this case, there's only 2 unknown variables. We have 2 equations, and so we can solve this out, and that's what we do. We use simultaneous equations, and before I do that, of course, I know what cosine 45 is in my calculator, and I know what cosine 30 is in my calculator, right? 0.707 and 0.866. So I can go ahead and plug those in. And that first equation reduces down to this, which if I finish solving it for one of those variables, I can find out here that T1 equals 1.225 times T2. In other words, I've got to take the size of T2 and scale it up to get to size T1, which tells me what? T1 is a bigger force than T2. I've got to multiply T2 by a number bigger than 1 to scale it up by 22.5%, if you will, to get the size of T1. So T1 is ending up a bigger force than T2, but that's all the further I can go there. So now I turn in the second equation. Again, sine of 45 and sine 30, I can figure those out, right? And that's 0.707 and 0.5, so I can plug those into the equation, and then I end up with this equation, all right? I end up with that equation. Now, that's 2 unknowns with only 1 equation, but since I know this is true, I can make a substitution. I could say, well, in place of T1, I'm just going to write in 1.225 times T2, right? If T1 is equal to 1.225 times T2, then where I see this T1 here, right, I can just substitute in 1.225 T2. And when I do that, I end up with 1 equation with 1 unknown. And now it becomes a matter of solving the math, right? 0.707 times 1.225. And then I add on 0.5, and I end up with 1.366 T2 equals 100, which then I solve out, and I find out, oh look, T2 is 73.2 pounds. All right? Once I have that, guess what? Well, now that I know T2, I can take the 73.2 pounds, plug it in there, and I can now solve out for T1. And when I do that, I find out that T1 is even bigger than 73.2. It's 89.7 pounds. Okay, so we had a 100-pound, let's say, football stadium speaker hanging there, right? And we had two basic support ropes tied to the ceiling. Notice that, if you take 100 divided by 2, it's only 50. But both of these ropes have far more tension in than just 50 pounds. It's not like one of them is going to be less than 50 and the other one bigger. No, they're both bigger than 50 pounds in this case, right? In other words, T1 plus T2 adds up to greater than 100 pounds. And that's because those tensions were at an angle, right? So when we tie things on, hang things like this, it's really important we understand the physics of this, and we can solve out our engineering equations and stuff to get the right tensions in these things. Because if we buy the wrong strength cord, obviously if that speaker falls, it could kill someone. And so typically in engineering, when you have you have what we call safety factors. So looking at this, I would say, well, gee, 100-pound cable would probably be okay, because neither of these tensions are going to be bigger than 100 pounds. But usually what we do is add in safety factors. So I probably wouldn't recommend a 100-pound cable. I would say probably use 200 or 300-pound cable, right? But now if human life is at stake, right? If human life is at stake, it's not uncommon to use safety factors anywhere from 10 times to 30 times. Because where there's human life at stake, you don't want your thing failing and killing anybody, right? If it could kill somebody if the thing breaks. If that speaker's so heavy, 100 pounds, and it's hanging above somebody's head at a football stadium, and that thing were to break and fall, that could be a disaster. And so in this particular case, we might end up, we might recommend a 2,000-pound cable or something like that for this situation. And the reason why is you're going to say, well, why does it have to be that large? Well, because you don't know, as engineer, you'll find out as you continue to take engineering classes that you don't always anticipate what people are going to do. And so when there's human life involved, you add in safety. You add in these big safety factors. So at a football stadium, for example, if there's a bunch of fans down here and they're drinking beer and getting all excited and their team just won a big game, sometimes people will do crazy things, like this guy will climb up on this guy's shoulder and then say, oh, put me up on the speaker, and then they start standing on the speaker and hanging from the speakers and cheering and swinging on the speakers and things like that. Or the wind's blowing, or maybe snow comes down and coats the top of the speaker and adds weight. You don't really know. It's hard to anticipate every single thing that could possibly happen that you didn't think of. You're probably going to forget something or miss something. And so you add huge safety factors in there. But one key thing here is, I've had students say, isn't there an easier way to do this problem? Just by knowing the angles. Just by knowing that this one was 45 and this one was 30, isn't there an easier way you can get to these answers? And the answer to that is no, not really. There's no easy way to get to that. You have to break the forces into component form and do the math of it all to figure out what the tensions are. Okay? Anyway, so there's how you do an example. There's an example of a Newton's law type question, one in which we did not have any acceleration, where we had an acceleration of 0 along each dimension. And so again, that's called a statics problem. So you practice as many of those types of problems as you. So that problem wasn't too bad. Some of these problems can get quite complicated, but let's deal now with one that has acceleration in it. Okay, we just dealt with the statics problem, so now let's deal with one that has some acceleration. And again, when you're learning these techniques and problem-solving strategies, it's always important to start with problems that are relatively straightforward and simple. And so a very common problem in introductory physics textbooks is to use this, or to do what they call an Atwood machine problem. Okay, not every introductory physics book has this in, but many do. Okay, and the Atwood machine is a very, very simple machine. And what it is, it's basically made of a pulley up here. So let's say it's a massless, frictionless pulley. And then we have an object of mass m1 here, and another object of mass m2 here, and there's a rope connecting them, or a string connecting them, hanging over the pulley. So if one of these masses is heavier than the other, let's say m2 is heavier than m1, then when we release this thing, m2 is going to go down, right, and m1 is going to go up. So it's a very simple motion. It's a very simple machine, but we could lift a lighter object with a heavier object using this sort of a contraption. So this is a famous arrangement, or an arrangement that's commonly referred to as, again, the Atwood machine. Okay? Now there's two basic ways we can solve this problem out. Again, we assume that the rope or the string here connecting the two is massless, or has negligible mass, and we're assuming that the pulley itself has no friction and no mass as well, so that the pulley wheel will turn completely with no inertia or resistance to motion at all. Now, when if you're anything like me, when I first saw this, I was like, well, isn't this just going to accelerate at g? You know, with no friction, isn't this thing just going to fall down at 9.8 and this one go up at 9.8 meters per second squared acceleration? Well, you might think so, but that's not the case. And you'll see why as we continue through this. It'll hopefully become apparent. See, this object, if we cut the thread there, yeah, this one would free fall, right? If we cut the thread there, this one would free fall, right? And they would free fall at 9.8 if we ignore air resistance. The thing is, the weight on this one is trying to accelerate this mass, but it's got this other mass kind of dragging behind that we have to lift up. So this thing is not going to go at 9.8 meters per second squared. So acceleration here is not g, if that's what you were thinking. Now, there's two basic ways to solve this sort of problem, and we're going to look at both ways. And your goal is to try to understand both ways, but hopefully, you know, one of these will make more sense to you, and you probably want to use that strategy most of the time. Okay, so in method number one is a little bit of a physical trick to make the mathematics and problem solving easier. And it will work with this kind of a problem. So I want to show you method one here first. So mass M1 and M2, we don't know their masses. We're going to leave everything in variable form here. It's not uncommon, again, to start solving problems with no numbers in them. Okay, you want to start practicing that in this course. You'll find as you go up into higher levels of physics and science and engineering that more and more your problems will ask you to solve for answers that are expressed in variables rather than actual numbers. And the reason for that is once you've solved the problem with variables, you've got a little cookbook answer in variable form that you can then plug in whatever numbers you had at the beginning of the problem. If you solve it with certain numbers, you get an answer at the end that says a number, but then if somebody gives you different numbers, you've got to retrace back through the whole problem to get your answer. It's a little bit like kind of what you're having happen in WebAssign, where I solve the problem with one set of numbers, and if you get a different set of numbers, it's like, oh, to get my answers, I got to like trace back through what Mr. Trout shows in his solution with my numbers to get the answer. So the better way is to eventually get comfortable enough at doing everything algebraically with just variable letters, and your answer will turn out with the variables as part of your answer. And then by changing variable values, you don't have to redo the whole problem. You just have the answer already expressed. So anyway, so we have M1 and M2 for the mass of the two objects. We've got the tensions here. Again, I've drawn the tensions in here in a direction that is expressed on the object. So in other words, if I look at object M1, what direction is the tension in the rope acting on it? Well, if M2 is heavier, then tension T here is pulling upward, right? And I know what's pulling downward on the ball? Force of gravity. In other words, the weight of the object, M1G. Same thing on the other side. M2 has a weight M2G, and the tension on this cord here that's acting on it is pulling upward as well, supporting it. Obviously, if I cut that rope again, it falls even faster. So the tension here is obviously upward and resisting the fall of block 2. But let's assume here we're told that the acceleration direction is downward for the block on the right and upward for the block on the left, and that's apparently because M2 must be bigger than M1, right? And so, but because this string connects them, because we have this massless string connecting them, whatever rate A goes down at, or I mean M2 goes down at, say A is just the magnitude of the acceleration here. So A is the number we're giving for the size of the acceleration, and A here is downward for the right one, then it would be the same size acceleration over here for M1, it's just in the upward direction, right? So there I've got my diagram all sketched out. And what's the next thing to do? Draw a free body diagram. Now, when I go to do that, remember that I get to define my system, or what objects I'm focusing on. So what object am I focusing on? Well, it's the whole thing, really, right? I mean, the tension's the same throughout the whole rope, and the acceleration down is the same as the acceleration up there. So, like, what point's better than any other? I certainly don't want to accept the pulley because the pulley's not going anywhere. I mean, there's no motion happening. So if I'm looking, though, at these forces in the acceleration, the objects of interest are these, but there's two of them. So what do? Do I draw two free body diagrams? That's one method, right? But the method I want to show you here is to actually kind of define the system as being both masses together, right? And to do that, we pretty much have to kind of straighten up the system. So if you could imagine this pulley, the center of this pulley up here being like a hinge, we're going to kind of unfold, you know, if you could imagine kind of unfolding the system, like right now it's bent over that pulley. Well, what if I were to pull this side, this block up like this until it's all the way horizontal, and I pull this circle thing up all the way till it's horizontal, then I could actually draw this as a straight line problem. Okay, I don't know if that visually is making sense or not, but maybe if I just go ahead and kind of show you what I'm doing. So in this diagram I have here now, what I've done is unfolded the system where the pulley was. In other words, I've said, well, who cares about the pulley? But the pulley would really be like right here between the two blocks, right? And I just kind of unfolded it as if it was like a hinge there. And I straightened the problem up. And when I do that, then I put a dotted box, you notice my dotted box here, I put around objects M1 and M2, because they're both going to accelerate at the same rate. As a matter of fact, if I unfold it like this, they're both going to be accelerating to the right, right? I mean, if you're visualizing this right. And so what I did was I combined both masses there. Now, once I put that dotted box, really what I'm saying is anything going on inside that dotted box now, I really don't care about. It's almost like I'm thinking of the dotted box now as being one object, right? That dotted box is now my system. I'm analyzing this system here. And so the mass of my system is just M1 plus M2, right? It's the mass of both things inside there. The pulley and the rope didn't have any mass. So M1 plus M2 is the mass inside my system. And I only have two forces involved here now, right? I've got my M1G that's pulling that direction, resisting the motion, and I've got M2G pulling to the right. It's trying to make the system go, and M2G is going to win, obviously, because the acceleration here is going to be that direction. So anyway, I've got it all unfolded, and now I just apply Newton's second law of motion, which says that the net force, how do I get the net force? Well, I have to add up the forces involved. There's these two forces involved. But keep in mind the direction, right? When we have a coordinate system, remember our sign convention, to the right is positive, to the left is negative. Right? Just like you learned a number line when you were in elementary school or an x-axis in algebra class. And so M2G is positive and M1G is negative. So when I say, hey, what's the net force? My net force here, okay, again, following the law, second law of motion, M2 minus Mg is my net force, right? M2 to the right, positive, M1G in the negative direction. So M2G minus M1G is my net force. I set that equal to the mass of my system, which is now M1 plus M2, times the acceleration of the system, okay? If I want to, I could factor out a g here. I've got a g factored times or multiplied by m1 and m2, so I could factor that out, right, and express it that way. And then solving this out for the acceleration, I find out the acceleration of the system here, the rate at which this thing's going to accelerate, is m2 minus m1 over m1 plus m2 times g. In other words, this fraction of the acceleration of gravity, g, is going to be the rate of acceleration. So if m1 had zero mass, it makes sense. If m1 had no mass and a string has no mass, then m2 would have no mass dragging behind it. And what would we get? m2 over m2 times g, or 1 times g. It would accelerate towards the Earth at the rate g if m1 was not existent. In other words, if none of this existed back here, it would just free fall, which makes sense. If m1 equals m2, we would expect this to go nowhere. And take a look at our fraction. m2 minus m1, if these are equal, what do we get up on top of the fraction? 0. And it would say, hey, no acceleration. So here we have our acceleration for the system in cookbook form, which is very nice. Again, the g stands for 9.8 meters per second squared. And m1 and m2 are the masses. In typical standard units would be kilograms, but notice because we'd have the same mass units above and below on this fraction, it really wouldn't even matter. We could find the masses in grams, put the units, the mass units in grams here, and the grams would cancel the grams, and we'd still end up, as long as we're using g in meters per second squared, we'd get our answer for acceleration in meters per second squared. Okay? Now, once I know the acceleration, if I have an expression for the acceleration, then how do I figure out the tension? Well, now if I go back and I just look at this one object here, so I kind of start the problem over and say, well, now I know the tension, or I know the acceleration, and the tension here, you know, I'd basically have a free body diagram that looks like this. I'd have tension upward, and I'd have my weight force M1G downward, and this is M1, right? And my net force would be T minus M1G, and that would equal the mass M1 times the acceleration, which is this amount. So if I plug all that in and I solve it out, I could get the tension in the cord as well. So in other words, the tension, I could write the expression and say, well, the tension is going to be M1 times G plus A. That's how it'll all work out when you do all that math. Okay, so the tension is equal to M1 times G plus A. So now we've got an expression for the tension as well. So that was one way to solve the problem. But there is a second way that's just as valid and is actually a little more mathematical and a little more, let's say, disciplined without having to use this little trick of unfolding the system. You can solve this problem straightforward. You'll just end up with simultaneous equations, and that's okay as well. So let's show you how to solve this problem with method 2, and that is where I consider both objects individually, and basically I treat it as two problems. I've got a problem for object M1 on the left side here, and I've got a problem for M2 on the right side. But I do know that the problems are connected together because the tension here, this being a massless rope, will be the same as the tension over there. And since they're connected by a rope, whatever rate M2 is accelerating downward, A is going to accelerate upward at that same rate. So we do have some connections in the problem, but otherwise I'm going to analyze them as two separate systems. So if I look at system 1 with M1, I look and I see I got a T upward and an M1G downward. So my net force for system 1 is T upward minus M1G. And the mass of my system is just what's inside my dotted line, which is M1, right? And then the acceleration here is in the positive direction, so I just put in positive A. And so my equation reads like this. It says T minus M1G equals M1A, or in other words, T equals M1A plus M1G. And if I could factor out the M1, then I can write it as T equals M1 times G plus A. You'll notice that's the same equation we got on the previous slide, okay? Looking at the leftward block. So we end up with the same basic equation. Now, over here in system 2, now I've got T upward and M2G downward, so my net force here is T1 minus M2G. The mass inside my system 2 is just M2, and my acceleration here is an amount A, but it's in a downward direction, so I put that in with as minus A. Again, if we're using the letter A to stand for the size of the acceleration, right, then the acceleration here is going to be a minus A. All right, so again, signs are important. So anyway, solving this out, I end up with T is equal to M2 times G minus A. All right, we do a little bit of algebra and we get that. Notice that that is a different expression. However, we do know that this T is the same as this T, don't we? All right, if it's a massless rope, the tension throughout this massless rope is the same. That's our rule, and it's a good rule. It helps to simplify the problem a little bit here. So these two tensions are the same, so now we have simultaneous equations. We can say, well, M1 times G plus A has to be equal to M2 times G minus A, right? And what's this do? This gives us a single equation with a single unknown of A. Remember, the assumption here is that somebody's going to tell us M1 and M2, and we already know G, right? So we really would know everything in these equations except A. And so now I've got this, because the two tensions, the tension I got here and the tension I got here are equal, we end up with this equation, which now I can solve out and get my acceleration, and guess what? Get the same answers we did on the previous slide. Acceleration is the amount M2 minus M1 over M1 plus M2 times G. So after we do our algebra, we get the same answer for the expression for A. Up here, we got the same expression for T looking at that system, plus we have an additional expression for T that's true also from system 2. But you'll notice in this particular method, we get the right answer, and we just dealt with it as two separate systems, and we looked at things that were equivalent in two systems so that we could bring them together and solve it out. So that's method 2, and there's nothing wrong with that method. That's just as good or perhaps better in some ways as the first method. So either method in this case solves the Atwood machine problem. Here's another problem somewhat similar, except the blocks are sliding along a table. Well, the one block sliding along a table. This is from your book, And I will leave it to you to read through these couple of slides in your lecture PowerPoints. Notice that the book does it in a very similar way, except they analyze both blocks as individual systems, much like our method number 2, and they arrive at their answers for this particular problem. So that's another example you should read through for yourselves. I don't really want to take the time right now in this lecture to go through all the details, but as you notice, you end up with some cookbook formulas there, the way they analyze this, and then you can solve out and get answers for that problem. Here's a question that's interesting. It says, suppose that a clothesline is stretched between two trees. The clothesline is 5 meters long and can be considered massless. There's a 3-pound weight hanging at the center of the clothesline. How much tension must there be in the rope in order for the clothesline to be stretched perfectly horizontal? Okay, so you may want to think about that for a few minutes, maybe pause the video. And if you've had some time to think about this, hopefully you came to the conclusion that it's actually impossible to stretch anything with mass perfectly horizontal in a gravitational field. Okay, so if we had this weight hanging here, there's no way with just horizontal forces we could balance the downward pull of this object. Remember, if things aren't moving, we have to have an equal amount of force upward here to balance the weight. So this weight here would always have to have some upward component of the force, right, in the tension of the rope. The rope would have to go up at least somewhat, okay? The smaller this angle here, the smaller you make this angle, the bigger the tension you would need, the longer these tension vectors would have to become in order to offset the weight downward of the block. All right. So in other words, if you draw this to scale, right, what I'm getting at here is if these ropes had bigger angles, then let's suppose the weight has this, the weight vector is that big. Then we just need each of these vectors to be half as long, so that when I add this amount to this amount, I end up with this amount, right? So with big angles, it doesn't take a whole lot of tension for that to happen, right? If I lower the angle like this, then to get that amount of height that I need to come out here further. The tension forces have to be bigger because the angle's smaller. So as I make the angle more and more narrow, these tension vectors have to get bigger and bigger. In other words, the tension forces are going to get huge. And theoretically, the tension would go to infinity as you start to approach this 90-degree angle where we would have perfectly horizontal. So this is an impossible situation. So even with a real rope, if we think of a real rope or a real string hanging in a gravitational field, there's always going to be some curvature in it, okay? Because this little section of rope here with a real rope has a little bit of mass, has a little bit of weight downward, right? And so we're always going to have some curvature. As a matter of fact, if I cut out a bigger piece of the rope, it has an even bigger mass, so the angle has to go up. So when we hang a real string in a gravitational field, it will always arc like this, and the ends of the rope will be at a higher angle, and the center of the rope will be level, but you will always have some upward pull off the center, so the string will always be curved. Now, if you pull a lot of tension into a very light string, a lot of people working construction and so forth will do what they call snap a chalk line or something, where they take a string that has chalk on it and they stretch it very tightly, and then they snap it to get a straight line across the wall. Or maybe they stretch a light string with a lot of tension in it to provide a guide for building a wall or something like that to make it level. So you can get it very close to level, right? I mean, you can get it very close to straight. But if you look really carefully along a string that's stretched tightly between two posts, if you're in a gravitational field, that will always curve just a little bit, right? It's always going to curve just a little bit because you're going to need a little bit of upward pull for this section here. You're going to need a little bit more upward pull for the bigger section of the rope. So as we go out, the curve is going to get steeper. And so there's a special shape, a mathematical shape for that actual curve of a string hanging between two supports in a gravitational field. Okay, and that's more of an upper level physics problem to solve out for that curve because the mathematics get a little more complicated. But anyway, that's an example of a conceptual question. And hopefully if you reasoned it through right, you realized that it was impossible. Now I think we're going to flip a few slides ahead here since we're getting close to the end of the lecture time. And let's take a look at an example that's will give you a chance to practice some of the things you've been learning in this particular lecture. It says a block with a mass of 10 kilograms is pulled along a frictionless table by a hanging ball with a mass of 5 kilograms. Determine the acceleration of the system and the tension in the cord. Okay, the pulley is frictionless and massless, and you may also ignore the mass of the cord and assume that that's negligible mass or zero mass. Okay, so I want to know how fast is these blocks, how fast is the green block going to accelerate to the right and the ball downward, and what is the tension in the cord. So you may want to pause the video, work on this, and then resume to see how you did. Okay, so hopefully you started by drawing yourself a diagram, something of the sort I show here. I used method number 1 like we used for the Atwood machine, and I unfolded the system where the pulley is and made it a straight line problem looking at both masses moving together, both M1 and M2. This allowed me to solve for the net force of M2G and set that equal to the mass of the system, M1 plus M2 times the acceleration of the system. Solving out for the acceleration, then I got M2 times G over M1 plus M2, which if we put in the values for the mass of the blocks and the ball of 10 kilograms and 5 kilograms, and we put in for G 9.8 meters per second squared, I find the acceleration of the system as 3.27 meters per second squared, which I can then use looking at the block, M1, and I know that the tension force, looking in the x direction, the tension is the only force pulling in the x direction, so that has to be equal to the mass of the system, M1, times the acceleration in the x direction, which is the acceleration of our system. And so knowing the acceleration of our system is 3.27 meters per second squared, multiplying that by the 10 kilogram mass, I find that the tension has to be 32.7 newtons. If you plug that 32.7 newtons in for T, you could solve the system for the ball falling as well, and you'll find that the acceleration using that tension will be 3.27 meters per second squared in the negative direction. And so it all comes full circle and works. So hopefully you did well with that problem. You need to continue to practice these sorts of problems in your homework and in the book. Do as many of these types of problems as you need to. If you need extra problems, of course, the internet is full of all kinds of simple F equals ma or kinematic or dynamics questions. And again, you practice as many as you need and ask me as many questions as you need to get good at this stuff. Okay, but I think that's where we'll end this particular lecture.